What happens if the lessons on time? Alright.
We'll see. Alright, so today we are going to talk about where a derivative might fail to exist. Okay? So, everything we've looked at so far, right, the derivative has existed everywhere. Okay? Everything we've looked at so far, the derivative has existed everywhere. So today we're going to look at 4 different cases where the derivative may fail to exist. Okay? No. No. This is different. Alright? So, the first place that a derivative may fail to exist is if our function has a corner, okay, a sharp edge. Okay? Now, there are a couple of ways that we can think about why this would fail to exist. Right? This is just the absolute value of x, right? A pretty straightforward, simple function. So, at this corner, if we think about trying to draw a tangent line, okay, and remember we said a tangent line is a line that approximates the slope at a point on a graph. Right? So if I tried to draw a tangent line at x equals 0, where would I draw that tangent line? Would it look like this? Would it look like this? Would it look like this? So I hear one person says like that. Okay, why couldn't I draw it like that? Right? It's right along that line there, right? Well, I could draw it like that, right along that line too, right? I could draw the tangent line anywhere there. Okay, that's why the derivative fails to exist, is because there's not one place to draw the tangent line. Everything we've done so far, right, we've had some smooth curve, and we said, well, if I tried to draw the tangent there, okay, there's only one way to draw it. Okay, if I tried to draw the tangent here, well, that would be something like that. Okay, if I tried to draw the tangent up here, it would be something like that. There's no debating that, right? There's only one way to do it. At this point here, there's a whole bunch of different places I could draw the tangent line. Okay? That's why we say the tangent or the derivative fails to exist at that point. Okay? Another way that we can think about this is if we actually look at the derivative. Right? So this is the absolute value of x. This piece over here, okay, where x is less than 0, is just a straight line. Right? This is y equals negative x. If we just take a look at this piece over here, what's the slope of that line? This is algebra 1. What's the slope of that line? Almost. Am I going up or down? Negative, right? The slope of this would be -1. So if I wanted to sketch my derivative function, okay, and I know we've only done this one day, right, trying to sketch a derivative from an original graph, okay, and we'll do this a lot more, but if I were to sketch this derivative, right, the slope everywhere here is -1. It's not changing. The slope is always -1 over here. So my derivative is just at -1 here, right? Now over here, at everything greater than 0, what's my slope? +1, right? This is what the derivative function of this would look like. It's not defined here because there's a big jump in the derivative, okay? The slope changes immediately. In order for the derivative to exist, it has to be a smooth curve. It's not. We immediately jump from a slope of -1 to +1. There's nothing in between. So we say that the derivative doesn't exist there, or the function is not differentiable there. Alright? Make a little bit of sense? Okay. The second way that a derivative might fail to exist is if there is a cusp. Okay, this is pretty similar to a corner. Okay, a cusp. You guys getting all this? Just remember it without notes. Right.
I got that first one on my head.
Forget. Take some notes. Alright. A cusp cusp is just kind of like an extreme corner, right? It just, looks like it's going to start going to negative infinity, and then this side kind of looks like it's going to start going to negative infinity as well. It's just a more extreme corner. So the same idea applies here, right? I'm going from a really steep negative slope, and then I immediately change to a really steep positive slope. Okay? There's no smooth curve there. Okay, so I cannot differentiate at a cusp. Okay? So why don't we try to sketch the derivative of this guy as well? Okay? My slope everywhere over here is negative. Right? I'm going down everywhere over here. So that tells me I'm going to be below the x-axis on my derivative over here. Well, I'm starting off with a kind of shallow negative slope, and I'm getting steeper and steeper and steeper. Right? So that's saying, well, I'm going to start off with a small negative value and keep getting more and more and more negative. Right? So my derivative to the left of 0 might look something like that. Okay, now over here, I'm starting off with a pretty steep positive slope, and then it shallows out. Okay, so let's say I'm starting up here with a high value, and it's getting smaller and smaller and smaller, but still positive. Okay, so my derivative might look something like that. Okay, and again, we can see that at x equals 0, at this place where there's a cusp, there's nothing going on with the derivative. Okay? The derivative is undefined there. Okay with that one? Fantastic. Okay, the third way that a derivative might fail to exist is if we have a vertical tangent line. Okay, if any place on the graph has a vertical tangent line. So right here, again, in this case at x equals 0, and if I were to draw my tangent line in there, it would be completely vertical. Again, if you think back to Algebra 1, what's the slope of a completely vertical line? Undefined, right? That's why our derivative is undefined if we have a vertical tangent line. Okay, remember, derivative is just a function that tells me the slope. So right here, my derivative would be undefined. Okay, and this is one of those parent functions that you're supposed to have memorized, right? The cubed root of x, or x to the 1/3 power. You're supposed to, right? Alright, so if we wanted to sketch the derivative of something like this, okay, that might, again, help us see why that doesn't exist there. Okay, so the slope is always positive here, right? Everywhere the slope is positive. I never have a negative slope here. But here, my slope is pretty shallow, right? It's pretty close to 0, and then it gets steeper and steeper and steeper until it's actually going straight up. So over here, my slope, my value is pretty close to 0, and it starts just going steeper and steeper and steeper. It starts going straight up. Well, over here, my slope starts incredibly steep and then starts shallowing out. Okay, so starting with a really high value, and then it starts to shallow out. So my derivative would look something like this. Okay. So, 3 ways so far that a derivative would fail to exist: a corner, a cusp, or a vertical tangent. Okay, the last one. Oops, did I go too far? I did. Is a discontinuity. Okay, a discontinuity. If the function is discontinuous, it is not differentiable there. So this is a really simple example. Right? You get a jump discontinuity here at x equals 0. The function is not differentiable at x equals 0. Right? Again, we could try to sketch the derivative of this curve. Actually, they called this u, so this would be u prime, not f prime. What's the slope of this piece over here where x is less than 0? So that's slope. the value of that function is -1, but the slope is 0. Right? The slope is 0. So if I'm sketching my derivative, that would just be at 0. We know it's not defined then at 0 because we've got a discontinuity. Then what's the slope of my line over here? Also 0. So again, my derivative is just going on the x-axis there. But we know there's a hole at 0 because it's not differentiable there. If it's not differentiable, I know there's going to be a hole in the derivative. Okay. So, 4 ways that a function might not be differentiable: corner, cusp, vertical tangent, or discontinuity. Questions on those? All right, then let's try a few more examples here. All right. So on the homework, there are a bunch of graphs. Okay. Some give you a function and say, are there points where the function is continuous but not differentiable, differentiable but not continuous, or both? Okay. So let's try something like that. Let's say that's at x equals 3. So at x equals 3, is this function differentiable? No, right? It's discontinuous. If function's discontinuous, it's not differentiable. Right? Is it continuous? No, right? We just said it's discontinuous. Okay? There are questions on the homework like that, okay, that ask you, is it differentiable? No, it's discontinuous. Well, is it continuous? No, it's discontinuous. Right? What about something like this? So again, say that's at x equals 3. So at x equals 3, is this function continuous? Yeah, right? Is it differentiable? No. Why not? We've got a corner, okay? How about... Is my function continuous at 3? Is it differentiable at 3? Yes, right? It would be a smooth curve. I can draw a tangent there, okay? There are also problems on the homework that just give you an equation, okay? On those, some of those, you should be able to do by hand, okay? For example, what if I give you something like 1 over x plus 2? Are there any points on that graph where the function would not be differentiable?
Yes.
Where?
-2. Just
-2.
kidding.
Right. At x equals -2, I will have a 0 in the denominator, which means I'll have an asymptote, a vertical asymptote at -2. So what type of discontinuity is that? Corner, cusp, right? Discontinuity. Right? An asymptote would be a type of discontinuity. Okay? So in this function, we know it's going to have an asymptote over here. It'll actually do something like this. So we can say it is both discontinuous and not differentiable at -2. Okay? There are some other problems in the homework where I just give you an equation. Okay? And those are a little bit tougher to visualize. Okay? If you come you come across one, right, where you don't have any idea what the graph looks like, get graphing calculator and graph it, right? Remember, a free graphing calculator, okay, either on your Chromebook or on your phone, Desmos. Right? You could either go to desmos.com on your Chromebooks, or you could download the Desmos app from the App Store or Google Play, or whatever phone you have. Okay? That's pretty much it. Any questions?